Hello, thank you all for coming. Today, my name is Dori. I'm CTO at Incredibuild. Today we are going to discuss multi-process versus multi-threading. Which one do we need to choose and which considerations do we have on choosing one over the other? This is a topic which is usually not addressed. And when you have a new scenario, a new application, or a new model in which you want to decide which architecture best suits your need, there are a bunch of considerations. We have a lot of experience in that, in choosing the right architecture for you. There are benefits and disadvantages for each of these architectures. And in today's world, in today's multi-core world, and in today's world of scalability, making the right decision is very important, both for the time to market of your product and even more for the future of your product. So before we delve into the consideration we need to take, let's discuss a little bit about Moore's Law. So Moore's Law had the assumption that the processor clock time will be doubled every 2 years. This was very good for a long time. But things have been reduced in the past years. We can see that the clock time doesn't improve as it used to have before. And Moore's Law is going to come to an end quite soon. And the way that vendors have coped with this is by introducing multiprocessor. So in today's laptop workstation, everyone has 4, 8, 16, 32, 64 cores. And that's how the vendors cope with Moore's Law reaching its limits. And this is where the vendors are going forward. So if you once were able to rely on improvement in clock speed, saying, OK, I can develop my application as it is. Tomorrow I'll buy a new hardware with better clock time. I'll get double the performance I had. These days are gone now. So you can benefit from that. So in order to benefit from multi-core technology, you now need to think more before making architectural decisions in order to make sure your application, your execution can benefit from this multi-core technology. So you need to think, how am I going to write my application? How am I going to encapsulate my object, my classes, my business logic in order to actually benefit from multi-core technology? Multi-processing technology. So we'll start with multi-threading. We'll start with the pros, with the benefits of multi-threading. So I assume that everyone knows what's a thread here and what's a process. I'm not going to speak about that, just the considerations that we want to take after we know these basic elements. So we'll start with multi-threading. First, it's easy and fast to share data and to communicate between threads. Everything is shared memory. You can easily access code using variables, classes, objects, etc., in order to communicate, sync, and maintain state in your application in a multi-threaded application. It's also very easy to communicate with the parent process, the process that invokes the threads, get back the output that the thread generated, and maintain state with the parent process. It's beneficial if you have large data sets. So we have scenarios in which you have a very large data set that you want to get into the memory, and all the threads are working with this data set. So multi-threading is good there because you don't want to duplicate your data set if you have multi-process. So if you have multi-process, you need to duplicate this data set for each process, which can take time and memory, and this is not the best solution for you to do. There are solutions on how we can share, even in a multi-process architecture, data between processes, and we'll discuss that as well. But it's quite easy to do that with multi-threading application. The last thing, the major benefit is that multi-threading is supported by a lot of third-party libraries, open source and commercial, allowing you to quickly to develop multi-threads. I think that the next session in this room is about OpenMP, which is one of the best solutions I know for multi-threading development, and I really recommend listening to it. So the cons of multi-threaded, and I don't know how many of you have developed multi-threaded, but it's a bit complex. One of the major drawbacks is that if one of your threads crash, your entire application will crash. This is not a good thing. And if you have a lot of business logic in the threads, and the threads are complex, it's very complicated and hard to debug. If you'll have a bug in multi-threaded application, that's a problem. Okay, race conditions, some kind of things overriding data. This can be a pain. It takes a long time. Usually, the debugger is not the best tool to manage, to handle bugs in multi-threaded application, and you need to have logs in order to really find where the bug is going and which thread overrides the other. And this is a real pain. So if you think that you have a complex scenario, having it in a multi-threader, you need to understand that you'll have bugs, okay? Everyone have. It will take you longer to fix them. It also requires better, more experienced developers in order to implement and develop multi-threaded application in a correct manner. Newbies developers, I don't know if I would give them a large and complex multi-threaded execution to develop. Another thing we need to take under consideration is that if we have too many threads, we will waste a lot of time in context switching. Okay, the CPU will context switch all the time, which will make us lose performance. And this is not something we want to have. And another thing that is not written here is that if we have multi-threaded application, all the threads are using the same process memory space, which is very good if you want to communicate between the threads because it's very easy. But if we need more memory, if each thread requires more memory, we have a limitation there, which we don't have in a multi-process execution, which each process gets its own allocation of memory space. Another very important thing, and it's very important for today when we're speaking about and we see the adaptation of cloud computing, and we see we have a lot, not only my machine is 8-core laptop, all the machines in my network are 8, 16 cores, virtual machines with multiple cores. Scalability is very important if we are speaking about large problems that needs to be solved, and we'll discuss that further on. So, multi-process. When we're saying multi-process, it doesn't mean that we are not doing multi-threaded. So you can have applications which are both multi-process and multi-threaded. In fact, Incredibuild is both multi-process, multi-threaded, multi-machine, which is the most complex environment you can think of. But this is feasible. This is doable, but it requires a lot of expertise in order to achieve that. If one of your processes crashes, it doesn't mean the entire application crash, unless your process is in the kernel level, and then you're in trouble. But usually it's not that scenario. So this is very nice, and it allows you to encapsulate your business logic, and if something fails, you can recover. You can recover, and this is something we also do. We have multiple processes. One of our processes failed. We know that it failed. We just re-execute it elsewhere, and we try to recover from this scenario. It's much easier to debug. So it's much easier to debug a small atomic process than debug an application which is multi-threaded. You usually have less locking issues in which that you need to be concerned about, unless you try to implement some kind of shared memory between processes. So I've discussed this before when we spoke about multi-threaded. We said that multi-threaded use the same memory, and it's very easy to do that. And if we have things that require a lot of data to be initialized, multi-threaded is easy it's something that it's easy to achieve with multi-threaded applications. But you can do the same with multi-process. So you can have shared memory and all the processes accessing the same shared memory area, but that will require you to have your custom development in order to do that. You need to maintain your own locks, semaphore, mutexes, things like that, in order to make sure nothing, you don't have any race condition and things like that with the data. And last thing, it's very scalable. If I have multi-process, I can scale I can execute, if I have a lot of processes, I can execute them elsewhere. I can offload them to a remote machine. I can offload them to the cloud. I can offer this as a service to my customers. This is another benefit that you have in multi-process application. So the drawbacks, as we said, is the communication. Communicating between threads is, between processes is more complex than doing it within threads, okay? Usually you'll go for something like TCP/IP or other kind of communication protocols, but these protocols are not efficient in terms of performance as shared memory. So if you really need performance and multi-process, you'll need to implement some kind of shared memory that all these processes can access. This is feasible, but complex. So you can do that, but this is not as easy as doing it in multi-threaded development. And of course, you have a smaller set of supporting libraries that allow you to have some kind of process safe, like you have thread safe arrays and structure for multi-threaded application. For multi-process, there are less libraries that offer these kinds of solutions. So after just giving a high overview of these two concepts, I want to outline a list of considerations that I think you should have before taking a decision which architecture suits you most. So the first thing I consider usually is the syncing. So do I have a lot of syncing? Do I need to maintain states between processes? So for example, and I will give examples in the, later on, if you have something like artificial intelligence and you have multiple threads, usually in artificial intelligence, these threads are communicating between each other. And they are communicating a lot, and you need to maintain states and a lot of other things which make it more complex. Do I have large data sets? How large is my data? Can I break my data into smaller subsets? And this is very meaningful, as we discussed before, because we don't want to duplicate the data we initialize in the memory. Who is going to develop this? Is it newbie developers? Is it experienced developers? Because maintenance can be a pain later on. And also the way that the application is developed, the way that the code is developed, you can do everything. You know, you can do a lot of things using not the best techniques, and it will work, but then it will break later on. It won't be as scalable. And of course, scaling. How much am I compute intense? How many tasks do I need to spawn in parallel? What's the scope of my problem? And what will be the scope of my problem in the future if my startup or application will succeed, which is where we want to go. So we'll break this down. Synchronization, state maintenance, as we said, is easier in multi-threading. It's easier to debug these kind of issues in multi-threading. In multi-process, in order to do that, you need to have a custom development, whether TCP/IP, mutexes, semaphores, things like that, in order to communicate between the threads. It's more complex. Doable, but more complex. Another thing that we said is ease of development. So we have a lot of pre-made libraries for multi-threaded, and you can have a lot of structures and classes which are already thread safe, so you can use them in various threads in a convenient manner, and you'll know that you won't get into some race conditions, which is very easy. But debugging, maintaining, and code understanding is much easier in multi-process. Another thing is that multi-process requires you to maintain encapsulation, because you want to have each process having everything that it needs in its own source code, which is something that you need to consider when you're architecting your solution, but it's also good for the future, for your application. It's nice. When you have good encapsulation, it's very good. And bugs are usually less complicated to solve when you have multi-process execution and not multi-threaded, unless, again, you are having some kind of multi-process with shared memory and multi-machine and things like that, which makes it as complex as multi-threading. The last thing is throughput and scalability. So one of the things we need to consider before taking our decision is how many tasks do I want to execute in parallel now and in the future? Am I speaking about 2, 3, dozen, 1,000, millions? And I know of customers, our customers, that have millions of tasks that they execute in parallel. How much time does it take? Does it take milliseconds, 2 milliseconds to execute my thread and that's it? Does it take several minutes? Because these things really, they make an impact on your decision. Because if every task that you have takes only 2 milliseconds and that's it, maybe it's not, you can have a thread to do that. You don't want to waste even a little bit of time on initializing a new process, although this doesn't, the difference between initializing a process and initializing a thread, especially in Linux, is not that different. But if we are speaking about milliseconds, that's still something we need to consider. How much memory will my task require? If my task every task requires something like 500 mega of memory, then I will only be able to run something like 4 in parallel in the same process space. And then I might want to break that into multiple processes and not use threads. And furthermore, if I have a lot of tasks and they require a lot of memory, I might want to use distributed computing in the future. I might want to distribute these tasks to other machines in order to gain both memory and CPU power of not only the machines of my user, but also other machines, whether in the local network or the public cloud or cluster or any other solution that supports distributed execution. And if we're speaking about distributed execution, usually distributed execution can only happen if you have multi-process. You need some kind of small atomic element that you can distribute to a remote machine, that you can offload to the public cloud. You cannot offload a thread. You need something to wrap it. You need an executable, a process. So this is another consideration that we need to take. How complex is my tasks, is my business logic, is my task's business logic? If it's too complex, you will have a lot of time wasted in the future maintaining this multi-threaded. So if it's too complex, you really want to consider how you make it easier, simpler, how you encapsulate it, and maybe multi-threaded, multi-process is the solution for you. Is it real time? If your solution, if your system is real time, if your application is real time, you need to consider that as well. Would you benefit from scalability in the future or right now? If not, that's fine. If you only have 2, 3 threads, you don't need to do much, and you won't need to have any scalability in the future as well. And another thing is that you can consider, for example, there are a lot of solutions that have a very, very large problem scope, and they have several customers. They have the customers which have small problem scopes, and this is something that they can accomplish in 10, 20 minutes. And they have the large customers which have very large problem scope, which can take weeks. In transient analysis, for example, PSCAD, they have a solution that takes them something like 2 weeks to calculate, okay, the largest ones. And then you can sell scalability as a service. You can sell cloud services. You can sell software as a service. This is something you need to consider. Usually we don't see that when we start our application or our product or our startup, but we need to consider what's going to happen once we succeed. Usually you start with a small problem, and when you run your test, this is a small problem, but once you start getting commercial and getting some very, very large customers and large problem scopes, this is something that becomes an issue. Some general question. Do my tasks require special hardware? If I only can execute my tasks in the special hardware, I don't need any scalability. Or I can offer scalability, but probably my hardware is expensive. And if I do have this scenario, I can also think and say, maybe not all my tasks need this special hardware. So there are scenarios in which some of your execution requires special hardware, but most of your execution does not. And if you write it in a multi-threaded way, you'll need to execute your entire process in this special hardware. But if you'll execute in a multi-process way, you can have your main application running, and once you have a task that needs to run in a special hardware, you can simply offload it to this special hardware, and then share this hardware with many applications and many tasks that requires this special hardware, but only for a short duration of time. This will cut down costs. Another thing we need to consider is connection to the database. This is a general consideration we need to make. How many, if for example, if we have multi-threaded, we don't usually want to maintain a DB connection per thread. Maybe we want to maintain one per machine. And this is something we need to consider as well. So let's talk a little bit. So we've discussed this in general, but I want to go down to earth and speak about real scenarios, real decisions, which kind of application took the decision of multi-threaded and which kind of application took the decision of multi-process. What's the pros and cons and how can we see that today? I think that one of the easiest things that I could find was Maven versus Make. I'm not sure whether you're familiar with it, so I'll give you a short overview. Maven, these are both popular build tools. Maven is usually used to compile Java code, and while Make is usually used to compile C, C++, but it's also used to compile other languages as well. They are very common, both these build tools. They have many tasks, compilation tasks. You know, we have hundreds, thousands. Adobe, for example, in Photoshop, they have 20 gigs of source code for Photoshop. That's amazing. It takes something like 24 hours to build Photoshop on a single machine, 32 cores, something like that. These tasks are usually atomic. Compilation tasks usually are not dependent upon one another. You have high concurrency level, okay? They have minimal communication. They don't need to interact between one with another. And the data set is small, only small CPP files, some header files, things like that. That's not a large data set. And it's scalable, okay? You have hundreds of tasks. You can scale this out. So what I want to do here is to try and see which one of the products took the right decision. So Maven was single-threaded just a few years ago. I don't know exactly, I remember when. But recently they became multi-threaded, which is great because now instead of working on a single core, I can work on my 8-core laptop and utilize all 8 cores, but it's still only 8 cores or 4 cores. But it's still a progress. So Maven is multi-threaded. Users, as you can see here, I don't know if it's large enough, but users are asking from the Maven community, they are asking for multi-process execution. The reason that they want multi-process execution is because sometimes they have processes requiring more memory. The threads require more memory. They have a lot of threads. They have a 64-core machine, a single process running 64, 128. We have this kind of customers. 128 threads, you know, it takes a lot of memory. It crashes. Simply crash because you don't have enough memory to handle this. So if I break this into multiple processes, that's a solution. Another thing is that due to the fact that Maven is multi-threaded, no third-party tools can be used and can be developed in order to distribute the compilation tasks. So you will always be limited to the local machine you have, to the build server you have. If you have 16 cores, that's it. You won't be able to scale, you won't be able to offload, and this is another limitation that Maven has. Okay, this is how it used to look. This represents a single core here. And you can see this is how it used to work when it was single-threaded, just a very, very, very long task for your compilation. And this is how it works now. If I have a 4-core laptop, I can see that this is an example of Make, but the same thing it goes for Java, for Maven, and for Make. So whether it's a multi-process or multi-threaded, you'll be able to benefit from using all your local cores. As you can see here, tasks will be executed on multiple cores in parallel. So Make, as opposed to Maven, took the decision to be multi-process. In fact, most modern build tools are multi-process and not multi-threaded. Visual Studio, Scons, MS Build, WAF, Ninja, Jam, BGem, and a bunch of others. And the reason for that is better memory usage, easier development for them, and scalability. This is how it looks when you scale and distribute compilation tasks in Make, okay? This is the cores in my local machine, and these are cores on a remote machine. So there are solutions for Make, for example. There's this CC, Ice Cream, Incredible, which is where I work, that allow you to get distributed computing, both for builds and other stuff as well. Let me show it to you how it looks for, for real. So this is a build of Qt. I'm not sure, I believe that most of you heard about Qt. Qt is a very, very popular open source for doing GUI development, UI development. And on my 4-core, 8-core machine, it took something like 16 minutes. So if I would have executed it in Maven, it would have taken 16 minutes. If I execute it in Make, it takes more or less the same, 16 minutes. But it kind of, it uses all my cores. And let's see how important it is to have efficient parallelization. So it takes here something like 16 minutes, and I can look here at the monitor and see this space here. Do you see it? Sorry, I'm speaking and you're not seeing the. Let me see. How can I move it? Let's do this. 1 second. I'm trying to get this window in order for you to see it in the other screen. Here we got it. So this is Qt. Sorry, I just spoke and I didn't realize that you're not seeing my screen. So this is Qt, and this is a build of Qt, and as I said, it takes, I'll just minimize that in order for you to be able to look at it in a better way. So every line here represents a core, and you can see that Qt is being executed on all my 8 cores, whether it's multi-threaded or multi-process, and it takes 16 minutes to do that, okay? Every bar here represents a compilation or link task. But you can see here that I have something which is sequential, okay? So I can go and delve into that part, okay, and see what's happening here. Why am I not parallelizing my tasks? And I just zoom in. And I can see these mock steps. These are Qt steps that generates code that Qt then compiles. And I can see that when I'm using Visual Studio, Qt just executes these mock steps in a sequential manner. So I can optimize it. I can try and do it in a parallel fashion. If I do that, and I'll be able to do that, so I can see my build. Instead of executing this way, it can be executed in that way. So as you can see here, everything is very tight. Okay? Nothing is sequential. Everything is very, very parallel. And just by parallelizing in a better way, whether it's multi-threaded or multi-process, instead of having 16 minutes of build time, I can have 12 minutes. Which is very, very nice. We already reduced something like 25% of our build time, which can accumulate if you have a lot of developers compiling several times a day. But if you have multi-process, and this is where Make can go, but Maven cannot, you can have something like that. This is, again, the same solution, same Qt. As you can see here, these are the local cores. Usually when we are doing distributed computing, we don't want the IO-intensive task being executed remotely. So we will only execute link tasks on the local machine, because link is very IO-intensive. And we will execute all the compilation tasks remotely. And if you take a look, and I'll zoom out in order for you to be able to see, this now reduced the build time to 1 minute 40 seconds. How did we do that? So this is using distributed computing, which is the way that I can take processes, a lot of processes, and distribute them across machines, whether in a cluster, in the public cloud, in my local network, okay? And as you can see here, on your left side, you can see all the cores. But if I go down, you can see that I'm using right now 152 cores in order to execute Qt instead of only the local cores I had in my laptop. So just take a look. All these tasks are being executed on different cores across the local network, making my build time 10 times faster than it was before, just by distributing these tasks to other machines. So I can use my local network, I can use the public cloud, and this is the same kind of benefit you want your application to have, or the ability to offer this kind of benefit to your customers. This is only something you can achieve with multi-process. You can achieve this kind of functionality with multi-threaded in a easy way, or even relatively easy way. Just one last thing. If we go back here, one of the things that you can see in this, actually we can inspect and see. Look at here, look at the graphs here. I can see that in a specific area, okay, so you cannot see. Let's see if okay, the hints don't pop. But you can see here the blue line represents the number of tasks I have ready to be executed, while the red describes the number of tasks I actually can execute due to the number of cores that I have. So I can see that if the hint doesn't work here because of the second print screen, but here I have something like 700 tasks that can be executed, but I don't have enough processing power to execute them. So having distributed computing is really meaningful for these kind of scenarios. Okay, let's go back to the presentation. So this was the real life of Qt. Sorry for that. No. Great. So let's speak a little bit about real-life scenarios, real applications, and what did they decide to do with this kind of dilemma. So one of the sectors that used multi-threaded, and is good for multi-threading is the solution for that, is when you have large mesh, large data sets. For example, CAD, artificial intelligence, weather forecasting, genetic algorithms. These are applications that usually require bringing a very, very large data set into the memory. We are speaking about gigs of memory that we need to initialize. And then we have a lot of threads just communicating through this data. They are reading, they are writing, they are doing a lot of manipulation, and they communicate with each other. In this scenario, you usually want to have multi-threaded, unless you are willing to pay for the additional cost of development in order to implement some kind of shared memory between processes, which, as I said, is more complex, although it's doable. So in these scenarios, in CAD AI, you'll usually see multi-threaded application. And if we'll discuss real scenarios, so most of the CAD, the transient analysis simulation, large simulation, electricity simulation, what happens if this power plant goes down, what will happen to the entire network system and the entire electricity system. This takes hours, and most of them are multi-threaded, but you can see that there are some which invested in order to have the ability to scale, as we've seen before. For example, ANSYS, PSCAD, and there are just few of them, but there are some that offered some kind of multi-process scalable solution. Another area in which multi-threaded is usually used, but not all the time, is in real time. So if I have, for example, financial transactions, defense systems that need to just work on the fly, very, very fast, these are usually multi-threaded applications because you don't want to waste even a millisecond in initializing a process instead of initializing a thread and this communicating between the processes. But again, shared memory can fix that, but this is not the trivial solution. Another one is CRM, ERP, SAP, database application, okay? Usually all the business logic is in the database. It's not in the thread, it's not in the process, not in the task itself. So I just want to have this task does something with the database. Most of the business logic is in the database somewhere, and then I get the data back to my code, and then I put it somewhere. So there is not a lot of there is not a lot of business logic there. I don't need to develop multi-process. I just usually do some kind of query, stored procedure, wait for the results, bring the result back, that's it. Very easy, very simple. I don't need multi-process for that. So let's summarize. Multi-threaded, when it's good? It's good when we have simple scenarios, okay? I have a very simple scenario, a couple of threads, business logic, very easy. It's good for multi-threading. I don't need complex multi-process execution. Real-time applications. Long initialization time and very short computing time. So again, this multi-thread is good for that. Communication, syncs, states. These are things, if it's too complex, maybe multi-threaded is easier to develop. And if I have only a few highly intensive tasks, 2, 3, multi-threaded usually is good for that as well. Let's discuss multiprocessing. If I have large independent data sets, okay, not a single data set, several data sets. For example, financial derivatives, where I want to have end-of-day calculation for each paper. So I have each paper, I have the stock. Each stock is a different set of data. So this is classic for multiprocessing. This is classic scenario for scalability. Simulation, as I said, ANSYS, PSCAD, when we want to analyze a very, very big solution. But this solution can be break down. Maybe it's complex to break this down. Usually it is, okay? But this is something we want to invest in the beginning, when we architect the product in the beginning. Because doing that after we have the first beta or the first commercial product, that's it. You'll usually be stuck in multi-threaded forever. Rendering. Large video can take a long time. It's a large mesh, a lot of information, a lot of data, okay? But it can be break down. You can, render frames. You can render, instead of rendering the entire movie, just render 1 minute. So you have 90 minutes, 90 tasks, just distribute them. The classic for multi-process. It's not the same kind of data. Data set can be break down easily. When we have many calculation in small business units and small data sets, such as compilation, tests, unit tests, API tests, regression tests, stress tests, a lot of kind of tests, code analysis, asset builds, math calculations, in the banking industry, in the diamond industry, when they have millions of permutations with a very, very small data, but a lot of calculations, that's classic for multiprocess and for scalability as well. GPU. GPU is very cool. I don't know if you've experimented with GPU, but if you have this kind of problem that is good for GPU, the GPU gives, it's amazing. It runs so much faster than an average CPU. And today, with Tesla and other solutions that can provide you with concurrent GPUs on a card, okay, that's very beneficial. You can take your GPU calculations. Usually, if I have a laptop, I have a very inefficient GPU card, but I can offload that. So, for example, we've run some scenarios with password cracking, this kind of GPU stuff, which are very GPU focused. And you can offload, instead of executing this GPU task, and I have a lot of them on my laptop, I can have a single Tesla with a bunch of concrete GPU cards in it, and I can offload my entire process execution to this Tesla card. And then it will run so much faster than it will run on my desktop. Streaming. You're probably aware of streaming. Everyone is using that. Classic for multiprocess, again. And of course, the cloud, which is one of the buzzwords of today. And very, very, your CEO will try to generate more income. And I believe that if you're somewhere there, how can we have a SaaS solution, software as a service? How can we sell cloud services? This is where the world is going. Microsoft, for example, cloud first, mobile first, and a lot of companies are going there. And actually, the devices are becoming smaller, sometimes with less processing power. Application require more. Cloud is where the development is going. In this specific area, cloud is the future. I believe so. And we see that today. So in order to summarize that a little bit, so we spoke about architectural considerations. Can I break my execution into independent tasks? This is a crucial question, and we always need to consider that. Even if I don't want to have scalability, and even if I don't want to use multi-process or even multi-threaded, it's very, very good to write your code and to think about the future. Can I encapsulate? Can I break dependencies between my execution? And even write it in a way that will allow you, if you need in the future, to have either multi-threaded or multi-process execution, not even from the beginning, although it can be good to do it in the beginning as well. Can the work be divided on more than single host? Do we require? Is it beneficial? If I only have 2 tasks, scalability is not an issue. I don't need to do that. But if I have a lot of tasks, will I have a lot of tasks in the future? How many relations do I have in my data set and how large they are? This is something you need to consider. And you need to consider, again, the future. Because usually when you start, you have small data sets. And once you succeed, you have larger data sets. And how much time will it take my customer to execute a large scenario? So as I said, PSCAD, for example, or ANSYS started with small scenarios, small sites. But once you grow, and you grow international, you want to solve, instead of solving a problem of an electricity problem, transient analysis of a city, you want to go to the state. It's a very different problem in terms of, and it can be exponential in terms of the time it takes you to calculate it. Do I need some special communication and synchronization requirements? What's the complexity of my business logic? And will I want to have scaling to the cloud? Can I offer some kind of business value out of scaling some of my executions? There are a lot of infrastructures that allow you to get this kind of benefit when we're speaking about scalability. You have this in Hadoop when you're speaking about large data sets and you want to have distributed data, MapReduce. You have Univa Grid Engine with a proprietary dedicated grid. You have Incredible, which allows you to have ad hoc multi-process execution across network or public cloud. You have DCC for builds. You have a lot of solutions that you can use, whether in your application, whether you bring your application with such a solution to the market, to your customers, or in your development environment. So you have your development environment. Usually your build server takes a long time to execute if you have large solution. And when we speak and we sing Maven, so Maven started, Java, it started way back. Code was small, relatively small. Open source libraries that we used were relatively small as well. But 10 years later, suddenly our code is much more complex. We have much more source code. We use much more open source libraries, and we want to compile them as well. And this open source library, which had only a few units a few years before, now grown to something very, very large, which takes a long time. So Maven was very good in terms of multi-thread for 10 years ago. It's now kind of okay for multi-threaded, but you need to have more. I'm familiar with a lot of users that have Maven builds that take them hours. That's it as an overview. I'd be happy to take your questions and answer if I can. And if you have anything else to add, which I forgot, I'd be happy to add it to my presentation. I think that that's an interesting topic and it can help the community, and I'll be happy to share that. As I try to figure out and assemble this presentation, I tried to look in the web and see if there are other articles speaking about how to make this kind of consideration. I didn't find any. So if you have anything that I forgot here, I'll be happy to add it. Yeah.
I would add security to considerations.
Okay. So security in terms of multi-threaded versus multi-process?
Yes.
But when? Are you speaking when we want to scale?
Process isolation. So if you have a hostile, let's call it hostile workload, processing, if you have a bug in your, let's say, parsers or whatever,
yeah,
it will be exploited on a certain level. If you run it in a separate process that has lower privileges, like Chrome does.
That's a nice idea.
Sandbox.
Yeah.
That won't have as much of impact as it does when you're running in a multi-threaded.
Yeah. Thanks a lot. That's a great point. I didn't think about it. I'll add it as well. Anyone else? Yeah. One second.
Okay. In the past, I had to switch to multiprocess solution because part of the legacy code was not thread safe at all. So in order to execute more than one task together, I had to switch to multiprocess. And that's another issue that legacy code can drive your decision to.
Yeah. Thanks. Yeah, you're right.
Yeah, regarding multiple processor systems, across systems, I get the impression that most of them are using explicit message passing to change, you know, if it's across physical systems, so where you cannot do shared memory. But are you aware of systems that use distributed shared memory, like where the operating system's actually taking care of switching pages from one system to another?
I'm aware of one such solution, but it's a different solution. It's more of kind of low-level solution. They are called Scalable, and they have a way, a technology that aggregates your hardware and to make it a kind of a single machine. But this is done in the kernel level. Okay. So you can execute multiple processing, okay, as if you have a real 1,000 core machine, but that's also very costly, and that's the only one I'm familiar with. I know that there is another, just one second, I know that there is another experiment somewhere in the Tokyo University in Japan trying to do that, but that's still just the beginning.
I have somewhat related question. You mentioned that there are many multi-threaded libraries, of which I can think a number, but I don't know any multiprocessor libraries. Can you name any?
I can find some for you. I've seen some when looking at the web. Sorry?
Boost interprocess.
Yeah, Boost is actually a good idea. Every library that allows you to have communication protocols, easy communication protocols between multiple processors.
Well, communication protocols are communication protocols, but the library is specifically designed to build distributed applications, multi-processor applications.
Okay, so Incredible is one. You have some, for example, Univa have some kind of API that allow you to do some kind of distributed computing as well. There are a bunch of others, but as I said, not so many. I just found a little bit in the web, and that's what I said. There are just a few. Anyone else? Okay, thanks a lot. You are welcome to our booth if you want to have more information on how you can accelerate your development or your application. I'll be happy to answer your questions there. Thank you very much.